Hello, and thank you for joining us as we explore Elastic Cloud Serverless. Elasticsearch's new stateless architecture for speed, scale, and cost efficiency. I'm Bill Easton.
And I'm Yaru Lin.
And we're going to be guiding you through our new stateless architecture for Elasticsearch. But I'm not going to bury the lead. As of Monday, December 2nd, Elastic Cloud Serverless is now generally available on AWS. Elastic Cloud Serverless gives you hassle-free operations at scale with an architecture optimized for real-time applications. With serverless, low-latency queries, meet boundless storage, all backed by the full power of Elasticsearch. Today, we're going to be talking about how we got here, how Elastic Cloud Serverless is different, and why Elastic Cloud Serverless is the perfect addition for your next project. Data is messy, and there's a lot of it. It's structured, it's unstructured, it's images, documents, code, audio, and video. The sheer magnitude of the data is just enormous. As humans, we're approaching a zettabyte of information being generated every day, and there's no signs that it's slowing. That data isn't all in one place either. As our data grows, it inevitably spreads, influenced by availability requirements, mergers and acquisitions, network fees, data locality. Our data architecture becomes fragmented, with data sourced from different places, spread across many regions, and even cloud providers. With big data comes big responsibility. New requirements for data retention mean keeping audit logs for years instead of months. Fees grow unbounded as data piles up. Complexity grows as business requirements necessitate years of sensitive data, remain secure, but also instantly accessible. Teams are told to minimize cost, while the cloud talent gap ensures that solutions which require constant operational toil sit under-maintained, underutilized, and leave the full value of our data untapped. Data lakes promised to solve this problem, but they only come to the rescue if you're willing to wait hours for answers. Querying data where it lives can mean astronomical network fees. The Cloud Object Store now scales to 1 million buckets, but performance is slow. Security is difficult. Optimizing it is hard, and costs are really difficult to estimate. Data volume and data complexity are growing exponentially, and our existing data architectures are being asked to solve the problems of yesterday alongside the new demands of workloads like RAG and GenAI. With GenAI and semantic search, the value of unstructured data in your organization is now 10 times what it was just a couple of years ago. The math has completely changed, and we needed a new architecture that could support all of this and more while staying on budget. Elasticsearch, which has been traditionally known for speed and scale for search, was ready to be reimagined to handle even more data and larger and more frequent querying. The Elasticsearch architecture, as we all knew it, depended on a stateful system to store data within the cluster and to keep it available and searchable. This architecture involved Elasticsearch data nodes, which combined compute and storage, and handled both indexing and search. This familiar architecture with stateful data nodes is what enables Elasticsearch to rapidly index data and quickly make it available for search. One implication of this is that indexing and search share the same underlying capacity. With the same nodes handling search and indexing, contention is just inevitable. A sudden burst in indexing load could mean slower searches, or an operator loading a particularly complex dashboard could impact indexing performance. With both ingest and search sharing the same underlying hardware, optimizing that hardware requires picking the right hardware for what could be two very different workloads, and ideally without over-provisioning resources. And even once you have all that under control, availability becomes a key concern. Our strategy to improve availability and thus performance was by introducing primary and replica shards. Duplicating the data ensures that the data is always available, even if a node goes offline. However, duplicate data means higher storage cost, and ingesting data into primary and replica shards requires more CPU and further increases resource contention. When you index data, the data goes to a primary shard. The data gets indexed, written to a local solid-state drive. A copy is sent to a replica. The replica writes it to a transaction log and then syncs it to disk, another local solid-state drive. There's another system that writes the data into Lucene with segments. Every second, that system refreshes, and the recently indexed data becomes available for search. If I have 3 replicas or 4 replicas, I will be indexing the same data 3 or 4 times. And that data was all stored the same. It didn't matter if that data was new or old. It didn't matter how often you searched that data. The cost stays the same as the age of the data goes up. And the value of the data goes down. With this architecture, storing and searching old data costs just as much as storing and searching new data. So we introduced data tiering. Your valuable real-time data lives on the hot tier, on solid-state drives with microsecond read latency. Data that's no longer needed in real time moves to the warm tier, which could be on less expensive hard disk storage with millisecond read latency. As users moved more and more data to the warm tier, various features such as better compression were added to reduce data size and better handle the incredible volumes of machine-generated data. We introduced searchable snapshots, a way of storing data on object storage, which offered decoupled compute and storage. Storing data on low-cost object storage meant you could store a lot more data in the same budget, while eliminating the need for replicas. Object storage like AWS S3 has redundancy built in. Customers loved the ability to trade off price and performance, but provided feedback about the challenges of managing the data lifecycle, moving data between the tiers, and the amount of growing data in their cluster. To solve the data lifecycle problem, we introduced extensive index lifecycle management capabilities to automate movement of data through its lifecycle. Customers could define exactly how their data moves between tiers, ensure that they always stayed within budget, whether that budget was a certain dollar amount or a certain query response time. Customers finally had control over where their data lived, how it moved, how much it cost, how long it was retained for, and exactly what performance was available to them. So problem solved, right? We can just keep adding tiers, new storage options, and we can solve any use case at any scale. We could just keep iterating on this architecture and evolving it over time. At the same time, a number of things changed in the industry, especially when it comes to the architecture of data stores. The big change was a focus on cloud-native architectures. A big reason for this change is how mature cloud object storage had become. AWS S3 has extremely mature capabilities that allow you to build very sophisticated systems on top of it. Our customers were already moving petabytes of data to object stores. And we couldn't help but think, this S3 thing is actually pretty cool. And we're already leveraging some of its capabilities as part of searchable snapshots. So we started imagining a world where we wouldn't need to know how many microseconds it takes for a solid-state drive to respond to a read query. We would never have to worry about whether the index was stored on a 5,400 RPM hard disk or a 7,200 RPM hard disk, where we could depend on the reliability of that object storage entirely, without worries of local nodes going down, and while still being able to search through all of our data rapidly. So we had our work set out for us. We wanted to rebuild Elasticsearch for the cloud, while still providing all of the amazing batteries included that Elasticsearch is known for. So if we were starting from scratch, what would we do differently? Well, we knew this new architecture would rely on the cloud object store for limitless storage. If all the data was in an object store, we would never have to move it between tiers. We would never need to tier it at all. We could forget about the data lifecycle altogether. If all the data was in an object store, we wouldn't need to send indexing requests first to a primary and then to a replica. And there would be no limit to how much data we could work with. With a cloud object store, we would never need to over-provision storage to ensure capacity for new data tomorrow. In fact, we would never be provisioning storage at all. With storage scaling solved, we turned our attention to scaling compute. With stateful Elasticsearch, each node keeps state, like the translog, index, and cluster metadata is on a local disk attached to the node. And local state is hard to operate at scale. Everything is more difficult, whether you're scaling up or down, upgrading or restoring from failure. Each node starts looking more like a pet than cattle. So, we designed a compute layer that would scale as effortlessly as our storage layer. One that would make compute available exactly where it's needed, without significant over-provisioning, and without being susceptible to resource contention from mixed indexing and search workloads. This new compute layer would allow total isolation and independent scaling of indexing from search. This compute layer would ensure that spikes in ingest would never impact your search performance. And while Elasticsearch of today has no problem interacting with object stores, it still relies on local state for the translog, index data, and cluster metadata. And to be honest, this architecture has worked really well for Elastic, and there is a lot to like about it. But it does require that the primary store of data is a solid state disk attached to a server. So when you want to scale up or down, you have to move data from the disk of one server over the network to the disk of another server. While we've worked hard to make sure this is a reliable operation, you're still moving data from server to server each time you want to scale. And adding a new node doesn't improve performance until the cluster rebalances data onto that node. To truly achieve the speed and scale that Elasticsearch customers expect, we knew the stateful architecture was our next focus area. We didn't just want to make the object store where we store the data you index. We wanted to make the object store the primary place where we store all data in Elasticsearch. So the last remaining piece was to turn Elasticsearch stateless. Stateless Elasticsearch would have no problem scaling. It would gracefully handle node failures. Nodes could be treated like cattle and spun up or down in a moment's notice. All of the data would be persisted safely in the object store. Turning Elasticsearch stateless would require redesigning core components of Elasticsearch, including the translog, index, and cluster metadata. It would be a lot of work to do that. It would be a multi-year effort. So that's what we did. And to be honest, I'm going to spare you the details of every change that we've made, but I'm going to walk through just a couple. We redesigned the translog specifically for the cloud object store. To optimize object storage costs, we restructured the translog to aggregate writes per node and flush them to the object store every 200 milliseconds. This is really important for minimizing API calls. Additionally, instead of triggering an object store write for each refresh, we decoupled refreshes from object store writes by pushing refresh data directly to search nodes, deferring writes to the object store. This approach reduces object store API calls by 2 orders of magnitude while ensuring data integrity and cost-effective and efficient operation. We built a new backend platform using Kubernetes and Amazon EKS, leveraging Kubernetes native resources for container lifecycle management, scaling, and resilience. We developed custom controllers and services for provisioning, updates, and auto-scaling. Our architecture comprises of a global control plane for user and organization management and regional data planes using Kubernetes clusters in each supported cloud region to power the infrastructure. Every single day, users manage the size and capacity of their infrastructure for their hosted Elasticsearch solutions, adding, removing nodes, changing hardware profiles, and adjusting tier sizes. While this level of control is powerful, with Elastic Cloud Serverless, we wanted to offer a much simpler experience, one that would automatically respond to changes in usage, where the demand of increased ingestion rates or querying over larger amounts of data is what would drive the automatic scaling of a project. No longer is scaling just decided by how much free storage remains in your system. Whether the workload needs more storage, CPU, or memory, we ensure the right resources are available exactly where they're needed. Each indexing pod begins handling incoming documents, processing, transforming, and indexing them before flushing updates to S3. With Kubernetes as the backbone and stateless Elasticsearch as the killer app, we can scale the exact part of the project that needs it. Spinning up new pods is fast, and the new stateless architecture ensures they can begin handling requests almost immediately. You just start using it, and we make sure it always has the capacity to handle whatever you throw at it. Let's take a peek at how responsive this scaling is with some visuals from our own observability. On the left-hand side, we can see the indexing rate, a steady but steep increase that comes to a sudden stop. On the right side, we can see the stateless indexing pods being added to adjust to the growing load, and then at the very end, being removed quickly when the compute resources are no longer needed. So long story short, we rebuilt Elasticsearch from the ground up. Stateless, fully separated compute from storage, and we fully separated ingest from search. When you index the data, you index it once, because each document only touches a single indexing pod. Indexing is faster and more efficient. S3 handles the replication. When you want to search, you can have one search process, 10 search processes, or 1,000 search processes. They search on S3, which is obviously a little slower than local storage, but we can do smart caching and pre-fetch data to make sure the experience always remains interactive. My serverless project can suffer a loss of every underlying pod, and when the first replacement pod comes back online, everything starts to work again. And this new Elasticsearch relies on the same fundamental AWS services that you build your applications on. When deployed on AWS, your Elastic Cloud Serverless project runs on Amazon EKS and uses Amazon S3 for object storage, and it runs in the AWS region that you pick. I'll hand it to Yaru, who's going to show you the fruit of our labor.
Thanks, Bill. Now that we have heard Bill talk about why our new reimagined stateless architecture is so powerful and capable of handling the demands of modern workloads, let's take a look at how in action. And we thought that we would show you the results of some of our scale performance tests. So we'll look at performance both when it comes to index scaling and search query scaling. Now, these tests that we have built was for the purpose of this talk. So they're not fancy setups. They're pretty representative of the baseline experience that any user would have when you spin up an Elasticsearch project, serverless project. And of course, as Bill mentioned, we've already simplified the user experience significantly so that there are very few configurations for you to have to think about. But we don't tinker with any of that. What we do is we create a project, we use all of the out-of-the-box default settings, we point a few clients at the endpoint, and we begin to add data. And in the amount of time it takes the average person to maybe have lunch, we're able to add almost 4 billion documents. So for the indexing scale test, we wanted to simulate a situation in which the load is growing over time. So we started out with 12 Logstash instances that have 20 pipeline workers each. This is the maximum number of pipelines that Logstash supports. And each pipeline is processing events and sending them to Elasticsearch. And then 5 minutes later, we double the workload by adding another 12 Logstash instances. And then in 10 more minutes, we more than tripled the initial workload with another 16 more Logstash instances. So in the last 15 minutes, we increased the indexing load to a total of 40 Logstash instances and 800 pipelines. And now we are pretty representative of a very high throughput enterprise scale data ingestion mechanism. And since Logstash instances typically aggregate data from more than one source, this could easily represent the monitoring output from thousands of servers. We've also configured the output in Elasticsearch to be representative of data from different environments by writing our data into 10 different data streams. Now, data streams are a powerful approach to managing time series data because it has an integrated lifecycle management. And they're particularly robust in our serverless environment because we have automated and optimized shard management. So this is how serverless responds to our enterprise scale data ingestion. On the top, again, we can see the number of requests coming in and the actual HTTP response codes. And on the bottom, we can see ingest nodes that are being spun up in response. At any given time, when the ingest load is greater than what the ingest nodes can handle, we will send back 429 bulk rejection error so that Logstash knows to wait and retry later. And what we're doing in the background is scaling up very rapidly to be able to handle that load. But those 429s don't happen forever. And we're going to switch over to show you a a recorded video of our monitoring dashboard to see this happen. So the left-hand side, this is a bigger version of the screenshot that we showed before. You can see the responses and indexing rates on the charts on the left and the capacity that's being spun up in the charts on the middle. And we're going to wait for a bit, maybe fast forward through this video. So you can see that already we're getting past the 429 errors, the red bars. And this means that we're getting into the right scaling cadence to quickly adjust the increasing load. And I'm going to fast forward a little because it's going to look the same for a while. And what is really reassuring is that the indexing rates that we see on the left-hand side almost mirrors the capacity that we're spinning up on the right-hand side. I fast forward it. We're going to go all the way to the end when you see the indexing load actually dropping off. When that comes to a halt, what serverless does is wait around for about 15 minutes. When it detects that you have finished indexing, we will actually sharply drop off the indexing capacity so that you don't have wasted resources. In 1 hour, we managed to add 1.78 terabytes of data. But remember that our load increase has been gradual. If we used the peak indexing rate that we saw, we could have added about 4 terabytes of data in this hour. We also know that serverless is capable of scaling up beyond even this. At the maximum size of the ingest tier currently, we're able to handle about 144 terabytes of throughput per day. And now let's talk about what it is like to run search queries on terabytes of data. We used a serverless project that holds about 5 terabytes of searchable data, time series data spanning 7 days. And we have the project set up to the high throughput performance setting because we're going to really load test it. And we send a variety of aggregation requests and also our new ESQL queries to our serverless Elasticsearch instance. Similar to how we increase the number of Logstash pipelines that are sending data into Elasticsearch, we also ramped up the number of clients that are simultaneously querying Elasticsearch in this test. We started with 32, and then we went all the way up to 512 clients. Over a period of 2 hours, we saw that serverless Elasticsearch scaled up significantly on its search tier to accommodate the increasing number of clients. Our average search rate was about 900 requests per second, with a median response time of 36 milliseconds. And our peak search rate was over 3,000 requests per second. And again, even though these are quite impressive numbers, we didn't actually push serverless to its limits. Our search tier was, again, about 1.2 terabytes in size in memory, but we're capable of going even beyond that and handle an even higher search load. And finally, I just want to reiterate that the indexing and search scaling that we're seeing here happen completely independently of each other. This means that you could well be indexing terabytes of data at the same time as sending thousands of queries per second. And that's what's so magical about a stateless, decoupled architecture.
Thanks, Yaru. So if we put all of the pieces together, it would look like this. We decouple compute from storage and store all data directly in the S3 object store. We split search and indexing. We scale each independently as needed. Some projects need more resources for ingesting security or observability data. Some projects need more resources for real-time search applications, alerts or SLOs. Or maybe you don't ingest data on a petabyte scale, but you need the extra resources for vector search. Each tier automatically scaled to exactly what you need, exactly when you need it. With Elastic Cloud Serverless, we've also brought along all the components you know and love from Stateful, including Elastic Machine Learning, Fleet Service for centrally managing edge data collectors, the Managed Intake Service for application performance metrics, OTel data, synthetics, cloud security posture management, and more. Elastic Cloud Serverless projects are batteries included, and all of these services are available from the moment you start your serverless project. While I'm sure Fleet and Synthetics hold a special place in every one of your hearts, I'm personally partial to Fleet Service myself, the real reason we're doing all of this is to power our out-of-the-box solutions for search, observability, and security. Search provides the core components for search and vector database applications. Security combines threat detection analytics, cloud-native security, and endpoint protection into a single solution, so you can quickly detect, investigate, and respond to threats and vulnerabilities across your environment. Observability offers insights and context into the behavior of applications running in your environment. It's an important part of any system that you build and want to monitor. The Search AI Lake gives you all the advantages of a data lake without any of the disadvantages. It provides boundless scalability using object storage. It separates storage and compute. And independently and automatically scales indexing and search to perfectly fit your workload. Everything users know and love about Elasticsearch, with super fast search and data retrieval, support for all types of data, all the Elasticsearch APIs, including the newer ones around vectors, ESQL, and of course AI and ML capabilities. The Search AI Lake includes everything we're known for with Elasticsearch: powerful search, analytics, and speed. And it includes the things that we do well that we need to highlight more. We're a vector database, natively, and we have a wide range of AI and ML capabilities built as foundational parts of our platform. And the key and most impressive aspect, we were able to maintain these properties while bringing you the benefits of a data lake where we decouple compute from storage, independently scale indexing and search, and we transparently auto-scale every component of the platform to respond to your usage. So you need real-time, fast access to your data, and you need boundless scalability because your data is not going to stop growing. And you need rich query and analytics capabilities to be able to get to the right data. And if you want to be able to effectively compete today, your data needs to be Gen AI ready without adding yet another system. Elasticsearch Cloud Serverless checks all of these boxes. So focus on the things you care about and deliver value for your business. Whether you're using Elastic as a vector database, an observability platform, or a security SIEM, enjoy ultra-fast queries and analytics across all of your data. Enjoy lower costs and more reliable services with our new stateless architecture. Spin up projects as you need them, delete them when you're done. Elastic Cloud Serverless is fast, flexible, and easy. Leave the operations to us. And Elastic Cloud Serverless is not just infrastructure. With Elastic Solutions, Elastic Cloud Serverless is specifically tailored to solve real security, observability, and search problems out of the box. I'll hand it to Yaru for our last demo.
Thanks, Bill. So we're going to do a real live demo this time, and prayers that the demo gods will have mercy. We really wanted to show you just how frictionless it is and how out of the box it is to quickly get started on Elasticsearch. So this is the Elastic Cloud console. And the first thing we're going to do is show the creation of a serverless project, in case any of you have not seen it before. So we're going to click on Create Project, and you can see that we have project types that are tailored for your solution. Are you building an application? Are you here for observability? Are you here for security? The choice is very simple. We're here to build a search application, so we're going to click on the first option. And you can see that we have project configurations that are optimized for what you're trying to do. We have the general purpose configuration that's great for general use cases. If you're doing lexical search, if you're storing your logs. And then we also have a profile that is optimized for vectors. So if you want to heavily use vectors, this is the profile that we're actually going to create here. So I will call it reinvent, and then we will click on Create Project. And then we'll cheat a little bit and go back to our main screen because we already have a project set up for the purpose of this demo. We're going to open my demo project. Even though it has been created ahead of time, we actually have no data in this project. We're going to upload that together. So the first screen that you'll come to asks you to upload data. For a search data set, we can easily do that with the upload a file functionality. So we're going to click on upload a file. You see it's asking you to drag and drop the file that you want to add. We support a number of different formats. So we're going to drag over this cakes.json. I have a JSON that has some descriptions about the types of cakes that you can make and what kind of ingredients they entail. And you can see that my file uploader has picked up the number of fields I have. I have a detailed description field. I have a cake ID. I have an image, and I have a title. So for passages like this, if I index it as is and rely on the BM5 ranking algorithm, I might not get the most relevant answers when I want to find out what kind of ingredients can I make what kind of cakes with. So let's see how quickly I can get a little relevant boost from serverless. Let me hit import. We're going to call it cakes. Index name is going to be cakes. So this is called index mappings. It lists the number of fields that you want to create in your index. And the ones that we're really interested in are the detailed description, which contains a description of what cakes are made out of, and also the title of the cake. We're going to update the mapping. I'm going to copy that over here. So you see what I have done here is I have created a semantic text field for my detailed description. What this is going to do, once I import it, it's going to generate vector embeddings for that field. I'm going to click import. This is a very small file, so it should take only a few seconds for the file to be uploaded, creating a data view so we can take a look. OK, let's go look at our cakes in Discover. I'm going to pull up the details of one of the documents. And you can see here I have the original description about cheesecakes. It's a sweet dessert, and also its vector representation. And I know you're going to say, oh, this is cool. What am I going to do with all these vectors? We can get you to explore these vectors immediately. I'm going to hop over to our Playground app. The Playground app is an application interface we have set up for you to quickly explore your data via semantic search. I'm going to add our cakes index as my data source and save it. And what this is going to do in the background is when I issue a query, it's going to fetch the most relevant documents. As you can see, it has very smartly chosen the semantic fields that we have created, and we'll use semantic queries. So if I ask it, what kind of cake can I make with cinnamon? And it has fetched 3 documents and sent it to my LLM of choice and crafted an answer for me. It says, we can make both spice cake and apple cake with cinnamon. And if you wanted to see the source documents, it's easy to see the reference material on where spice cake uses cinnamon and where apple cake uses cinnamon. Let's ask it another question that's a little unexpected. What kind of cake can I make with lemon juice? Oh, so we can make carrot cake with lemon juice. And lemon juice can also be used in cake icing. I guess you learn something new every day at re:Invent.
Well, that was cool. Thank you, Yaru. So to recap, Elastic Cloud Serverless delivers simplified operations by design. It's fully managed and always up to date. We take on the responsibility for cluster optimization, index settings, upgrades, scaling, and maintenance. We get paged at 2 a.m. when something goes wrong, leaving you to rest easy. The same great experiences that Yaru showed you are available in serverless, hosted, and self-managed. We will meet you where you're at, whether you're deploying on Linux servers, Kubernetes pods, or on AWS. And we're actively investing in every deployment model to ensure that you're always in control of your data. Elastic Cloud Serverless comes in 3 flavors, each tailored to a specific use case. And our purpose-built solutions solve real problems, identifying the root cause of an outage across hundreds of services and billions of events, investigating threats like SolarWinds, which have a long dwell time, requiring investigation over significant amounts of historical data, or enabling generative AI workloads with retrieval augmented generation. Worry less and search more. If you care about simplicity, time to value, performance, control of spend, or you always need access to the latest and greatest capabilities, with our new Search AI Lake architecture, Elastic Cloud Serverless is the perfect tool for your next project. So try Elastic Cloud Serverless today. Scan the QR code to sign up for your free trial. Simply select a solution, search, observability, or security, and let us know what region you want to deploy to. No credit card is required. You can get started in minutes. And I mean, seriously, like 3 minutes. And you're in and playing around with serverless. Thanks for coming to our presentation about serverless. Enjoy the rest of your re:Invent.